So now we'll move on from basic inequality statements to what we call a compound inequality sentence. And if you recall, a compound inequality sentence is basically two simple inequalities either combined together with an and or an or statement. So this should look somewhat familiar to you from Algebra 1. You may need to review some basic rules here, but we need to add in here the idea of writing the solution set either in set builder notation or interval notation. Now, of course, we're going to continue to use more prominently interval notation, as that's what you'll be using more going forward. So we have a first example here that uses the and statement, and so I wanted to kind of point out a couple things in regards to the and statement. First and foremost, an and statement tends to give us what's called a bounded interval, which means that the solution set is not going to go to infinity. It's going to actually be broken off at certain endpoints in the solution set. And so basically how we would do this is we could solve each individual simple inequality separate of each other, and then actually graph the two separate of each other. And you can see in this example where we have the red graph and the light blue graph or the teal graph that individually they would basically overlap, and it's that overlapped portion that actually creates the solution set for this compound inequality. And you can see here in the diagram that it says and means that a solution makes both inequalities true. So since there's an overlap portion, the solution has to work for both inequalities. Now, if we have the same algebraic expression in both simple inequalities, we can actually collapse that down to a single range that we would use for an inequality, and you can see that example here down at the bottom. And so that's a good look at a and statement compound inequality. Now if we move down, what we'll see here is we have a compound inequality containing the or statement. Now again, we are simply going to solve each simple inequality by itself and graph each one of those separately. You can see in this case that the or statements don't have an overlapping portion. They both go towards infinity in the opposite directions. And so what this means is that the solution, whatever you get for the variable, can make either one of the inequalities true in any given particular situation. And so if you recognize that the and tends to create this bounded interval and this range bound interval, and the or statement tends to create two solutions that are going opposite directions to positive and negative infinity, you can quickly identify what type of compound inequality you're looking at. So, alright, let's go down and use those examples to help us solve sample problem number 3. So if you go ahead and take a moment to finish that and come back and take a look at the solution. Okay, so I'm going to work part A. We have an and compound inequality, and I'm just going to work it within the context of that. So remember, since we have it in collapsed form here, if I add 1 to the middle term, I also have to add 1, to both the outside terms as well. And so that's going to leave us negative 3 is less than 3x is less than or equal to 6. And now I will divide all parts by 3, leaving me negative 1 is less than or equal to x is less than or equal to 2. And so I have this compound inequality that's simplified. It's an and statement. So, and you can really look at this part here and see that the x is between the negative 1 and the 2, and that can really help me graph this. And I'm not going to get super involved with my graph here, but that's basically telling me I know it's all the values in between negative 1 and a positive 2. Since it's equal to, I'm going to be using the closed bracket off here, And I'm just going to use a highlight to represent the solution set. Now, to write that in interval notation, these brackets more or less drop down perfectly for my interval notation with the bounded interval using the endpoints as the numbers. So that is a good example of an and compound inequality. Now let's move on down to this or compound inequality. And again, we just want to work each of these simple inequalities separate of each other. And so I'll just go ahead and do that at this point. Okay, and you can see here that in the first simple inequality we were dividing by -3, so that changed our sign for us. And then in the second one it was just a straight inequality. What I did, instead of distributing first and then having to divide that 3 out later, I simply divided the 3 from the beginning to eliminate it. So I know I skipped some steps there to save some space. So now let's graph that solution. Again, here I can look at these individually and see, and you got to be careful. All the x values are greater than 2, and so it's not equal to, so that's going to be an open interval, and that's going to go on infinitely in that direction. And then, simply enough, x is going to be less than or equal to 0, so all values less than or equal, so I'm going to use that closed version, and the solutions will be moving that direction to infinity. Now, because of the fact that we don't have a bounded interval, we have 2 separate solutions, we have to write it that way. And so I can use the graph as a nice visual to write my solution set in interval notation. And so I have an open interval here with -infinity to 0, and then a closed one, and then an open one with the 2, and an open one with the positive infinity symbol. But since both of these are part of the total solution set, they can't stand alone individually, so we have to combine them together with our union symbol. And that's a pretty terrible looking union symbol. Try that again. So just the simple little U. So our interval notation would be that entire statement. Okay, so that's a good look at some compound inequalities.